Welcome to week 7 of problem solving sessions on the course finite element method and computational structural dynamics. In the previous sessions, we have seen how to determine the shape functions in the natural coordinate system and in the local coordinate system of a 2D element, right? And we have solved one problem in which the plate was subjected to the load on one edge by considering the 2D element, right? In these sessions, first I will show how the eight-noded element in the natural coordinate system can map the curved edges in the physical space of a 2D element, right? That means if this is your element, this is a four-noded element, and in this element in the physical space and the edges along the uh, edges between the nodes is linear, right? So for this type of uh, orbital element, we can easily map by using four-noded element or eight-noded element, right? But for the curve edges orbital element, you require at least eight-noded element in the natural coordinate system, right? This is what I want to show in this by using this first problem, right? So here I will show that how this linear edge of element of a 2D element in the natural coordinate system can represent the curved edges of a 2D element in the physical space, right? So this is the objective of this problem. So for that, I have taken 8 noded parallel element in the natural coordinate system, right? And the coordinates are -1, 0, -1, 1, -1. Similarly for the other edges also, right? So here first we, we have to determine the shape functions, and in the previous sessions we have seen how to determine the shape functions, right? And for this type of element, we have seen in the previous session that the shape functions for the nodes lying on the edge, it is very easy to determine, right? And from these nodes, with the help of these nodes, we can determine the shape functions of the nodes lying on the corner of 800 element. So for this element, we can write the shape functions easily, right? That is the shape functions for node 5, node 6, node 7, node 8. We have discussed this problem in the previous sessions, how to determine the shape functions. Right? So from this, we can determine the shape functions of a corner element by using these equations. Right? That is, here node 1, this is node 1, this is 2, this is 3, this is 4, this is 5, 6, 7, and 8, right? So this one node is surrounded by 5 and 8. The adjacent node is 5 and 8. So this 5 and 8 will come half of, we have to separate half of the node 5 functions or node 8 functions from the node 1 of 4 noded quadrilateral element. So this will give you the shape functions of node 1 of 8 noded quadrilateral element. In the similar fashions, we can determine the shape functions of node 2, node 3, and node 4. This we have discussed in the previous session also. I have just written node 2, node 3, and node 4. And once we have determined the shape functions, and we know that for the in the isoparametric mapping, The isoparametric mapping, the same shape functions or the same number of nodes is required to map the geometry to map the geometry and the displacement field, right? The same shape functions is required to map the geometry and the displacement field in the isoparametric mapping. And then by using the expressions, right, x is equal to summation of ni xi, where ni is nothing but the shape functions of a 8-noded quadrilateral element in the natural coordinate system, and xi is the coordinate of element. In the similar fashion, you can map the y coordinate, right? Yeah, ni is the shape functions of eight noded natural 8-noded quadrilateral element in the natural coordinate system, and y is the y coordinate of the element, right? And for this here, I have just taken one is, right? I want to say that this 2 and this is 5. Okay? This is the element in your natural coordinate system, and here I am taking the one element. And from the one element, I want to show, right, how this is representing the curve is, how this can be, this straight edge in the natural coordinate system can represent the curve edge in the physical space, right? That's why I have taken one edge only. You can take any edges, right? So for the explanations, I have taken one edge that is passing through one node 1, 5, and 2, right? So that's why, and we know that the value of eta here will be -1, and the value of all other nodes along on this edge will be 0, right? So from this, we don't have to write the other terms n3, n4, n6, because all this value is 0. If this will multiply the x coordinate, this will be also 0. So I have just consider n1, n2, and n5, right? And we have already determined the shape functions of n1, n2, and n5. That is the shape functions of node 1, 5, and 2, right? Once we will substitute the value of n1, n2, and n5 and the value of eta, that is -1, we will get the expressions for x in the terms of zeta. Similarly for y also, we will get the expression in the terms of zeta and x1 for y, x1, x2, x5 coordinate, and y1, y2, y5 coordinate for x and y mapping respectively. Right? And for that example, I have taken I I have taken the coordinate of uh, node 1, 5, 2, like this. The node 1 coordinate is 0, 0, node 2 coordinate is 3, 9, node 5 coordinate is 2 and 4, right? So once we know the coordinate, we will put the coordinate value here. So from that, we will get the value of x, y, x and y purely in the form of eta, purely in the form of zeta, right? So this is the x, and this is y. And x, y in the terms of zeta. And from these equations, we will eliminate the zeta, and the equations will turn out to be, once we replace the eta here, the equations is this, and this is, we know that this is the equations of a curve, right? And if you see all this, this curve is passing through all these points, right? If you want to check, you, you can substitute the value of p1 here, p2 here, p5, all will give you 0 here, right? This is, all these points will satisfy these equations, right? So from this example, we can show that this linear edge of a 8-noded element in the natural coordinate system can represent the curved edges of a 2D element in the physical space. Okay? This is what I was trying to show through this problem. Right? That the linear edges of 2D element having the 8 nodes can represent the curved edges in the of a curved edge of the 2D element in the physical space. Right? Similarly, if the edges are straight, that can be represented by either by four noded element, eight noded element, or a higher noded element. But for curved edges, we need at least eight noded element, right? So this is what I was trying to see here. Moving to the next column, in this we have to determine the isoparametric mapping, and then we have to find whether the mapping is valid for the uh, element or not. Right? Here this is the first element, this is the second element. The coordinate of first and second element is given. Right? And it is four noded elements, so here I have taken four noded natural four noded 2D element, the natural coordinate system, and you can easily determine the shape functions of this four noded 2D element in the natural coordinate system. Right? So the shape functions is like this. Okay? Node 1, node 2, node 3, and node 4. Determination of shape functions has been discussed in the week 6 sessions. If you have any difficulties, you can refer the week 6 8 sessions. Right? So once we have determined the shape functions, we know that for isoparametric mapping, we use the same number of shape functions, or the same shape functions is used to map the geometry and the displacement field. So from the equations, right, this is this one, value for y. And here we know that this ni is nothing but shape functions of a 2D element in the natural coordinate system, and xi and yi are the coordinates of the node, right? So once we substitute the value, here I have substituted the x coordinate. In the first equations, I have substituted the x coordinate of the first element. Right, this is the x coordinate of node 1, this is the x coordinate of node 2, this is the x coordinate of node 3, this is the x coordinate of node 4. Similarly, this is the y coordinate of node 1, this is the y coordinate of node 4, y coordinate of node 3, y coordinate of node 4. Right? Then I have substituted the value of n1, n2, n3, n4. That was determined or written in the previous slide. So once you substitute the value of n1, n2, n3, n4, you will get the x in the terms of eta and zeta like this. Similarly for y. The mapping in this column, the first column was to find the mapping. So this is how we do the mapping, right? We have done the mapping problem in the previous session also. So till this step, mapping is done. Then in the second part, it is asked to see whether this mapping as a parametric mapping is valid for this element or not. For that, we have to determine the Jacobian matrix, right? And this determinant of Jacobian matrix should not be zero within the element, or should not be negative within the element, for the isoparametric mapping to be valid within the element, right? For the determinations of this Jacobian matrix, we are calculating this x and y, right? Because the definitions from the definitions of Jacobian matrix, this is the summations of derivative uh, shape functions with respect to zeta eta multiplied with the xy coordinate, right? So this upper term we have already calculated here. This is nothing but x here. This is nothing but y here. So you can easily find out the Jacobian matrix by derivating this x with respect to zeta and eta, and y with respect to zeta and eta, right? So this is how you get the Jacobian matrix. So this is your Jacobian matrix having the element this one. This is right. So once we get the Jacobian matrix, we can easily determine the determinant of the Jacobian matrix. Right? So the determinant of Jacobian matrix is, so the first element is 275 eta minus 175 zeta minus 95 divided by 1600, right? And to find out whether this determinant of Jacobian matrix is zero within the element or not, we will substitute this 0 and we will determine the of region where this Jacobian matrix is 0. For that we will substitute this determinant equal to 0. From that we will get this linear equations in the terms of zeta and eta. Right? So eta is 1.6 times zeta minus 5.73, and if you plot this, this will look like a square, but I have drawn here by mistake. No, 90 degree rectangle. Um, and if you draw the equations of this of the region where the Jacobian matrix is 0, so this is nothing but the straight line that will pass through the point minus 5.73, and this point is nothing but 5.73 divided by 1.6. So this is larger than 3, so that's why I have determined I have drawn here. So this will pass like that. So this is the region where the Jacobian will be 0. So from this we can tell that the value of determinant is not 0 within this element, right? So from this we can see this, we can say that the isoparametric mapping is valid for this element. Similarly, for the second element also, we will do the mapping. We will substitute the value of shape functions and the xy coordinate in the mapping functions. Okay. This is the mapping, right? From this mapping, we can easily map the point or the displacement field on the natural coordinate system to the physical space, or the from the physical and local space to the natural coordinate system, right? And then to find out whether this mapping is valid or not, we have to determine the Jacobian matrix. And to determine the Jacobian matrix, we have to substitute the value of n1 and n2 and n3 and n4, right? And once we substituted the value of n1, n2, n3, 4 and took the derivative with respect to eta and zeta, we will get the Jacobian matrix like this. And once we will get the Jacobian matrix, we can easily find out the determinant of the Jacobian matrix. So this is 2 minus 211 zeta minus 296 zeta minus 209 divided by 800. And to find out the region where this determinant of Jacobian matrix will be 0, we will substitute this value to 0, which will lead to this equations, linear equations. And once we plot this one, this is minus 1, minus 1, 1, minus 1, and here it will be minus 7, 0.706, and it will be less, it will be 706 divided by 0.713. So this is slightly less than 1, so it will be within the element. So the equations of the region where this determinant of j will be 0 is this one, the red one. And from the figure we can see that this is within the element. So we can say that at some region within the element, the value of Jacobian matrix is equal to 0. So from this we can say that the isoparametric mapping is not valid for the second element. Right? So this is how you will solve this type of problem. Right? First, we will determine the functions, right, for the mapping, and from this we will determine the Jacobian matrix, and we will substitute this to 0 to evaluate the region where this determinant of Jacobian matrix is 0. Okay? Hence, we can say that the mapping is not valid. This is the third problem. In this, we have to find out the stiffness matrix of a four-noded 2D element, right, whose coordinate is given like this, and the Poisson's ratio and the Young modulus is given. So if we plot this element, so this is the first point. Somewhere if we go to second point, this will be, so this is how the element will look like, right? And for this element, we have to find out we have to evaluate the stiffness matrix, and to determine the stiffness matrix, first we have to determine the shape functions, right? And for this, then here I have used the natural coordinate system to determine the shape functions of this four-noded quadrilateral element. So in the in the natural coordinate system, this is the node 1, node 2, node 3, node 4. And in the previous sessions also, and in the previous slide also, we have seen the shape functions for the node 1. And with this one, shape functions for the node 2, shape functions for the node 3, shape functions for the node 4. Right? Once we know the shape functions, we can do the mapping by using the isoparametric mapping. Right? We have done in the previous column, we will substitute the value of n1, n2, n3, n4. That will get the x in the form of eta and zeta. Similarly, y also. And once we will get these mapping functions, we can easily determine the Jacobian matrix. Right? We solved this problem in the previous sessions. To calculate this derivative of x with respect to eta and zeta, derivative of y with respect to zeta and eta, this will give you the element of Jacobian matrix. And once we get the this Jacobian matrix determinant we can easily calculate from the matrix of the Jacobian matrix. Right? So once we get the Jacobian matrix, we can easily calculate the determinant. We have seen in the previous problem also. Right. And for the calculations of this is the basic formula, and for the 2D element, this volume terms we can convert in the form of dx and dy for the 2D element, right? And this further we can simplify for the natural coordinate system, right? We have replaced this derivative dx and dy in the terms of d zeta, eta and zeta, right? And we know that in the natural coordinate system, the variations of eta and zeta is from -1 to 1. That's why the integration is from -1 to 1, right? And for the calculations of this stiffness matrix, we need B, D, and J and T, right? For this problem, we can consider the unit thickness until unless the thickness is mentioned. This Jacobian matrix we have already calculated. So from the Jacobian matrix, we can determine the determinant of Jacobian matrix. Right? And for the 2D plane stain problem, we know the value of B, that is distance. And here in the problem, the value of Young modulus and the Poisson's ratio is given. So once we substitute the value of Young modulus and Poisson's ratio, we will get the D matrix like this, right? And B is the stage displacement relations matrix, right? And the value is And here we have considered the four noded elements. That's why we have 4 into 2, that is 8 degree of freedom. That's why the size of B matrix is 3 into 8. If you will consider the 8 noded element, so here degree of freedom will be 8 into 2, that is 16. So the size of the B matrix, that is stress displacement relations matrix, will be 3 into 16. Right? Here we have considered the 4 noded quadrilateral element. That's why the size of B matrix is 3 by 8, and the value of the element of this B matrix is this derivative of shape functions with respect to the zeta and eta, right? So we have calculated all the terms, B terms, D terms, T also, and the determinant of Jacobian, right? Here I have calculated the derivative of shape functions with respect to zeta and eta, right? Once you substitute each value, you will get the B matrix, right? Here in this problem, after calculating B, D, or all the terms, we can multiply all the matrix and we can integrate all the terms, right? From that you can get the stiffness matrix, or else you can use the gross quadrature instead of integrations, right? Instead of doing the integrations for the all element, you can use the gross quadrature to calculate the integrations value. For that we know that for the 1D element we can substitute the integrations in the summations form, where Wi is the weight functions and f zeta is the value of functions at the points, right? And n depends on the number of points we are using for the gross quadratures, whether it is on 1.2.3.5. So this is for the 1D uh, one dimensional integrations or the linear integrations, and this is for the two dimensional integrations. We can substitute we can substitute these integrations in the form of summations like this, right? Where wi and wj is the weight functions, and this will go. And here I have used 2 by 2 gross quadratures. So two lines along the eta, two lines along the zeta. Right? So the intersections will give you the 4 point. Right? So to evaluate the integrations, these double integrations, we have to do the summations, or we have to find the summations at this 4 integrations point. Right? We have to find the value at this 4 integrations point, and the summations will give you the stiffness matrix. Right? So, so once so here if you see uh, B matrix, the size of B matrix was 3 into 8, so the transpose will be 8 into 3, and the size of B matrix was 3 into 3, and the size of B matrix is 3 into 8, and T is some constant term, J is also some constant term, right? So ultimately the size of K matrix will come out to be 8 by 8, right? Because the degree of freedom is 8, right? That's why the size of stiffness matrix is 8 by 8. And we know that this is symmetric, so that's why I am not repeating the upper triangular terms, right? So you first you calculate the B matrix by substituting this value, then write D, then B, and you multiply these matrices and this T and J matrix. So you will get the every element in the terms of eta and zeta, right? And then do the by using the 2.2 2 into 2 gross quadrature, integrate at these 4 points, right? If you are using the 2 by 2 gross quadratures, then the weight functions will be 1 along this and along this also. So wi and wj will be 1, and this eta value will be plus minus 1 by root 3, then eta value will be plus minus 1 by root 3. So the combinations of these two values will give you the 4 points, and if once means you have to calculate the value of this matrix at this 4 point, and combine this will give you the element of this stiffness matrix. Suppose you want to calculate the k 3 3, so this element, so you will get this element, right, in the terms of eta and zeta, and you have to integrate from -1 to 1 and -1 to 1, right? One, either you can do the integrations or you can use the Gauss quadrature to evaluate the integrations terms, right? And if you are using 2 by 2 Gauss quadratures, you have to evaluate at this 4 point of integrations, and then you have to combine, and the combinations will give you the value of this element. Similarly, you will do for the all element, and in that way you can determine the stiffness matrix of this 2D element. Here I have taken the 4-noded 2D element. Similarly, you can calculate the stiffness matrix of the 8-noded element, 8-noded quadrilateral element, right? Or 3-noded or 6-noded triangular element. So here only I will finish the sessions. Sorry for the delay. My internet was not working. If you have any query, you can raise in the discussions forum or you can contact me. So I am ending the sessions here.